Hey everyone, welcome. I'm Alex, and I'm here with Ben.
Hey, good to be here.
So today we are tackling a really fundamental question in civil engineering. How do you actually design a sewer pipe that can handle everything a city throws at it? Believe me, it is way more interesting than it sounds.
Okay, so here's the problem you've set up for us, Alex. We've got a city, we know its population, and we know its water use. But how on earth do you get from that information to the physical size of a pipe? I mean, that feels like a huge jump. Where do you even begin with something like this?
That is the perfect question, Ben. And you're right, the logical place to start is to figure out the average amount of sewage that the city produces every day. But, and this is a big but, if we actually designed our pipe for that average, it would be a complete and utter disaster. That average flow is just the very first piece of the puzzle.
So yeah, our first step is calculating something called the average sewage flow, which we usually call Q average. Now, we don't actually go out and measure the sewage. Instead, we do something clever. We take the total amount of clean water the city supplies and we multiply it by a flow factor. It's usually about 0.8 or 80%. That just accounts for all the water that doesn't end up down the drain, like water for gardens or washing cars.
Okay, that makes total sense. We figure 80% of the water going in comes back out as sewage. But that brings me back to my question. If we have that nice, clean, average number for the day, why can't we just design the pipe to handle that? It seems like it would be so much simpler.
And that right there, that is the million-dollar question. Because people's habits aren't average. Nobody uses water evenly throughout the day. I mean, look at this. In the middle of the night, the flow is super low, maybe a third of the average. But then, think about the morning when everyone's getting ready for work or school. The flow can spike to 3 times the average. If our pipe was only built for the average, it would overflow every single day. We're talking raw sewage backing up into streets and homes. It'd be a public health nightmare. So we can't design for the average. We have to design for the peak.
Okay, so how do we deal with that massive spike in flow? We can't just guess or triple the size and hope for the best. No, engineers have a much more elegant solution for this. It's a really clever tool that lets us turn that average flow into a reliable peak flow number, and it's called the peak factor.
Okay, a peak factor. So it's basically just a multiplier we use to estimate that maximum or peak rate of flow. It's the number that accounts for the fact that pretty much everyone is taking a shower or flushing the toilet around the same time in the morning. You got it. Exactly. Just think of it as our safety multiplier. It's the thing that ensures the pipe can handle the absolute busiest moment of the day without ever failing.
Right. And one of the most common ways we calculate this peak factor is with something called Harmon's formula. Now look closely here because there is a classic trap that so many students fall into. See that note? The population, P, has to be put into the formula in thousands. So for our city of 50,000, you would use the number 50. If you plug in the full 50,000, your answer will be completely wrong and your design will fail. You have to watch out for that.
Got it. So P is in thousands. Okay, so we've got a way to calculate the peak flow from all the homes and businesses. But is that everything? I can't help but think there's other water getting into these pipes somewhere. I mean, what happens when it rains? Or what about groundwater?
You are absolutely right to ask that, and it brings up a really important distinction between 2 words that sound similar but mean very different things in engineering. The first is infiltration. That's groundwater from the soil that slowly leaks into our sewer pipes through tiny cracks or bad joints. It's always there, so we have to account for it in our design. The other term is inflow. Now that's a whole different problem. That's surface water, like from a big rainstorm, getting in through improper connections, like someone hooking up their roof drain directly to the sewer. That's a maintenance problem you have to fix, not something you design the whole system to handle.
All right, so let's take stock. We have our average flow, we have a tool, the peak factor, to turn that into peak flow, and we have our extra allowance for that sneaky groundwater, the infiltration. We officially have all the pieces we need. Now we just have to put them together to build our final design equation.
So it breaks down like this. Step 1, you calculate your average flow based on the water supply. Then, step 2, you use Harmon's formula to find your peak factor.
And then you just multiply those 2 numbers together, and that gives you the peak flow from people using water? Then for the final step, you just add on that little extra amount for infiltration, and that gives you the grand total.
And there it is. This is it. If you take one thing away from our talk today, this should be it. The total design flow, Q design, is the peak factor times the average flow plus the infiltration.
This right here is the core equation for all sanitary sewer design. It's the whole ball game.
Awesome. Okay, now that we have the master equation, I think we are finally ready to go all the way back to that first problem and actually solve it. I'm ready. Let's do this.
Okay, let's plug in the numbers. Step 1, the average flow. That's our 50,000 people times 200 liters per day times our 0.8 factor. After converting to seconds, that gives us 92.6 liters per second.
Okay, yep. And then for step 2, the peak factor, we use P equals 50, not 50,000. And plugging that in gives us a multiplier of 2.27.
Perfect. So you multiply that 2.27 by our average flow of 92.6. Then we just add a small, typical amount for infiltration and we get our final design flow, around 210 liters per second. That's the number we'd use to size our pipe.
And, it's so important to remember this. The formula gave us a number, 210. That's the science part. But the art, the real engineering skill, comes from knowing all the assumptions that went into that number. What we assumed about water use, about the condition of the pipes, about how the city might grow. The formula is just a tool. Real engineering is about judgment.
Wow, that really puts everything into perspective. Which kind of leaves us with one last big question for you all to think about. As our cities keep growing, as climate change alters rainfall, and as our existing sewer systems get older, how might engineers need to change or adapt this fundamental equation to meet the challenges of the future?